Imagine a race between two search algorithms digging through a massive database. Algorithm A finds the target in exactly 1 second. Algorithm B takes a painful 20 seconds. By every obvious metric, Algorithm A is superior. Except the test was rigged. Algorithm A had the advantage of a multi-million-dollar supercomputer, while Algorithm B was running on an outdated smartphone. This comparison exposes a massive flaw in how we intuitively think about software speed. Physical clock time is a contaminated metric, skewed by processor speed, background tasks, and operating system overhead. To actually measure code efficiency, engineers need a universal metric that strips away the hardware entirely to isolate the pure computational logic of the algorithm. To do that, we focus on the only variable that actually matters: input size. In computer science, we call this n. It represents the number of elements an algorithm must process. When we stop counting physical seconds and instead track how required computational steps grow as n gets larger, efficiency reveals itself as a mathematical property of growth. This mathematical growth is measured using Big O notation. Big O describes the upper bound of an algorithm's resource requirements, telling us exactly how bad the workload can become, the worst-case scenario, as our input size, n, increases. While omega measures the absolute minimum work and theta provides a tight bound, engineers prioritize Big O. When you are building massive systems for millions of users, you have to design for those worst-case guarantees. This diagram compares two data arrays to demonstrate O of 1, or constant time. Whether the array holds 10 items or 10 million, accessing a known slot takes exactly 1 step. The computational work remains identical regardless of the dataset size. Now, look at what happens if we don't know where our target is and have to scan the entire array. The work scales in direct 1-to-1 proportion with the data size. 5 items take 5 operations, 1,000,000 items take 1,000,000 operations. This is O of n, or linear time. As we scale, we apply the rule of constants. If an algorithm requires checking every item twice, technically 2n, we ignore that static multiplier. At a massive scale, only the dominant growth rate dictates performance. Big O strips away these superficial details to reveal the raw, unalterable trajectory of an algorithm's performance curve. This graph plots data size against the number of computational operations, and it shows what happens when code gets complex. The steady line is our linear time, but the violent spike is O of n squared, or quadratic time. This occurs when nested loops cause computational work to multiply against itself. Look at a stress test where our input is just 1,000 elements. A linear algorithm performs 1,000 operations, while the quadratic algorithm demands a staggering 1,000,000 operations to process the exact same data. Compare that to O of log n, or logarithmic time. This represents techniques like binary search, which cuts the remaining workload in half at every single step. Even as the data reaches into the millions, the operation count stays remarkably low. When a poorly chosen quadratic algorithm hits a real-world user base, the resulting cascade failure can cripple systems, regardless of how fast the hardware is. Understanding asymptotic scaling is the difference between software that serves a dozen local users and software that can serve the entire planet. But processing steps are only half the equation. Big O also measures space complexity, how much physical memory an algorithm consumes as the data grows. We distinguish between total space, the data itself, and auxiliary space, which is the extra scratch pad memory the algorithm needs to function. This creates the core strategic dilemma of engineering, the time-space trade-off. To reduce execution time, we often have to sacrifice memory, or save memory at the cost of extra computation. This balancing scale shows the trade-off. Linear search uses almost zero auxiliary space, but processing time is a heavy burden, dragging at O of n. We tip the scales using a hash table. By allocating extra memory to index data, we find things much faster. Using that extra memory successfully crushes the time complexity, from an O of n crawl down to an instant O of 1 lookup. Big O provides the precise framework engineers need to negotiate these limitations, allowing them to balance processing time against memory capacity to build the digital architecture of the modern world.